since you got so many references, and I don't want to hold you up, the next step is to kind of make a table trying to compare all the references for the multipliers. And actually, it's probably just better to do this in a video. So what you do is you make a table for each paper that lists each paper, and you have like the name of the structure, the technology, the voltage, current, range it worked, linearity, number of transistors, area, size, the year, quadrant, what kind of network was it in, and will it work? Which you might be um, hard for you to see right off the bat. So I thought let's just do the first paper, okay, which is artificial neural networks using MOS analog multipliers. So this one might not work because when they're talking about the multiplication, I think they're scaling some weight times a voltage. And so when you have these bias currents, you have a differential voltage, um, or these are the output currents. So you have these weights which you can digitally turn off and on, which then selects how much current will be flowing, and so you get a certain bias current, and then you have a differential current. Now the thing is we have a differential input voltage. Well, usually you're multiplying voltage time voltage. Here it's you have these weighted currents that there's four choices here, so there's 16 possible um, configurations if they're at different widths. Like if this is a 1 to 1 and 2 to 1 and 4 to 1 and 8 to 1, it's kind of like digitally weighted. Um, so really, you turn this off or on and get a current, which then you're multiplying that current by this. What makes me think that is in this chart, they're sweeping the voltage, and then, yeah, you get this kind of linear regime, but then it kind of saturates, which could be that's what they want because the multiplier, this kind of function looks like a thresholding function that other neural networks want, where really our whole neuron is switch, the threshold. But anyway, if you look through, they'll call it a two-quadrant multiplier. It's based off of currents, and down here, and some, yeah, you have to sometimes hunt, right? So the technology is 3 micron technology, and they give you the area. I didn't really see the power. Um, Gotta say though, this is pretty amazing work. Um, Doing it uh, this way, where you can have a differential signal here and a differential signal here, and then you're turning on the weights, and you can get a V out, right? Which is basically, is it on, is it off? Okay. But um, it might be worth thinking about where you have you have these currents, right? So you basically changing changing the voltage here and adjusting the currents. Have to think about it, but um, and I think this just might not be applicable. So in our thing over here, you could put maybe the network. If you go back and read the article, it's a Hopfield network. You might not know what that means, but you're just summarizing stuff. It actually says it's a two-quadrant multiplier, and I think we actually need a four because um, the squared function uses all the quadrants. 1990 area size of the resistors that's in there. This was 3 microns. 3 micron technology. Yeah, that's it's at least plus or minus 5 volts. Not quite sure if they put it in there. And they didn't really give their multiplier a fancy name, except you could call it multiplier circuit with 4-bit connection weight. I don't know. Um, but it's more, how like in an op amp you could configure it to have a gain of 1, 2, 7, right? In a way, that's what this is that the gains are multiplying some input signal, where we're asking like, no, multiplication of two signals times each other. Of course, what we're really going to do is have one signal squared. um, but anyway, I think this is the paper we started off with, and I gave it to you. But I think you guys are on the right track, um, and hopefully this helps you continue your literature review. All right. Good.